Hello and welcome back to Mrs. Ogram's Maths. Today we are looking at a practice paper for differentiation for Level 3 Calculus. This is not a real NZQA paper, but it is set up to be very, very similar to one, and it's the one that we used for our practice exams at my school. And that you pause before each question, have a go at it, and then watch the worked solutions. So this one we are differentiating this equation that we've got here. So this is two things times by each other, so we are going to use the product rule, which means that we differentiate one of the pieces. So I've differentiated e to the 2 minus x here, times it by the other piece, so the cos 2x doesn't change. Then we add on the opposite way round. So now we leave the e to the 2 minus x as it is, and we differentiate cos 2x, that becomes minus 2 sine 2x. There's no need to simplify your answers when you're doing the achieved questions, and in fact I recommend that you don't try to simplify them because you could potentially make some mistakes and you would do yourself out of a mark if you put a wrong answer after a correct one. Okay, next. We have this graph here, and I'm going to have to squeeze it up to be able to fit the question onto the same screen. So just have a look at that, pause, maybe make a note of the important points, and then we'll look at the question. Okay, so we're looking for the values of x where f dash of x is equal to 0. That means that the gradient equals 0. First of all, that only happens where you can work out the gradient, so any points on the graph that aren't differentiable won't be included. Okay, so gradient equals 0 means we can have a flat line or we can have a turning point. So here's the flat line here, and this graph goes off to the left indefinitely. So we've got everything less than 2. 2 is not included because the graph is not differentiable at 2. It's got a kink in it, so it'll be strictly less than 2. We also have a minimum just here. So at 4, that graph, the gradient is equal to 0, so it will be at x equals 4. So there's those two, x less than 2 and x equals 4. The second part, we're looking for when this graph is concave upwards. Concave upwards, I always try to remember this as if you're thinking about a bowl, if the bowl is upright, or if it's upside down. So concave upwards is the bowl is the right way up, concave down is the bowl is upside down. So if we look for where this is a graph that's the bowl is the right way up, then this is the general shape just here between 3 and 6. Now what we've got to look out for and be careful of is this little gap here. We actually have no graph where there's an empty hole. The graph doesn't exist right there. In fact, with the value of the graph is down here. However, this portion here was kind of looking like it was pieces of the same thing, but we had a stop and a restart at this bit of 5. So that means that our graph is concave up between 3 and 5, not including 3 and 5 because we've got an empty graph there, so the empty holes, and it continues to be concave up between 5 and 6, again not including 5, not including 6 because it's not differentiable just there. It could have been part of either side of that curve, so we can't say definitively it's concave upwards at 6. So we'll write them as two separate pieces like this, 3 to 5, 5 to 6, not inclusive on either end of those. For part C, we've got an equation of a curve right here. Again, it is a product rule. We've got two things being multiplied together. We want the x-coordinate of any stationary point. That happens when the gradient is equal to 0. So first of all, we need to work out the gradient. So we're finding dy by dx. We're going to do the first part of this differentiated gives us a 1 times by the second part, and then we add on the first part stays as it is, and the second part gets differentiated. So e to the x squared becomes 2x e to the x squared. We're going to set that equal to 0 because that's what happens when we have stationary points. Now, if you ever get a derivative equal to 0 with e to the something in it, try and factorize out the e part because that e part can never be equal to 0. It helps you to get rid of it. So I've factored out the e to the x bit here and then written the rest in this other bracket. Now that means that e to the x squared can't be 0, so this bit must be equal to 0 so that when they're times together we can get an answer of 0. Now we're solving a quadratic, so we put it into the quadratic formula and we get this result. X is minus 1 plus or minus 1 over root 2. And if you did it as a decimal, you would get those answers there, but it's not necessary to turn it into a decimal. I'm just writing this for completeness, if you like. I actually prefer to have the answer like this because then it's not been rounded. For part D, we have parametric equations. So you've got x in terms of t, y in terms of t. So we differentiate each one with respect to t first. So if we differentiate dx, we get 2t minus 2. And if we differentiate to find dy by dt, we'll get 1 over t minus 3. So just differentiating each of those terms. Now to find dy by dx, we will do dy by dt multiplied by dt by dx. So that means take dy by dt, flip over dx by dt so that it makes dt by dx and times them together. Now when x is 8 and y is 0 here, because what we're trying to do is find the gradient at this point here. So we need to work that through to find out when x is 8 and y is 0, what t would be. So either one of those can work to do this. I'm going to choose to use the y value just because it's equal to 0. It's probably going to be easier. So natural log of t minus 3 is 0. So t minus 3 is e to the 0. That means that t must be 4 because e to the 0 is 1. Anything to the 0 is 1. Okay, so the value at this point here, where x is 8 and y is 0, t is 4. So we can use that to put into our gradient. Okay, so dy by dx, if we put 4 in place of t, we end up with this just here. That comes to 1 over 6. Now we're trying to find the gradient of the normal. This gives us the gradient of the curve, which is the gradient of the tangent. The normal will be the negative reciprocal of this. So therefore the gradient of the normal is negative 6. Okay, so we've got a rates of change question for part E. Take a pause to read and understand the information being given. So I'm going to label up some pieces here. We've got h being the height and r the radius of the small cone inside. And the volume of a cone is given by this formula here, and that's what we're trying to maximize. To do that, we need dv by dr. We need to be able to differentiate that thing, set it equal to 0 so we can find a maximum point. Which means that we will need h in terms of r and substitute it into here, because right now we can't differentiate this because it's got two different variables in there. However, we know that those two are related to each other, so we can turn one into the other, or in terms of the other, and then we can go ahead with our differentiation. So take a look at this diagram up here. This is how we're going to do it. So the base and the height are in a ratio of 3 to 1. Now if we call this bit of radius r, this bit is h, then this bit left will be 3 minus h. Now since they are then similar triangles, 3 minus h will be equal to 3r. That proportion there will still be in a 1 to 3 ratio. So h can be rewritten as 3 minus 3r. So if we pop that into our formula for v, let's just move that up a little so I've got some space, then we're replacing the h with 3 minus 3r. Now we have everything in v in terms of r, and we can differentiate with respect to r. So first of all, multiplying that out, we're going to then differentiate each of those terms so we can get dv by dr. Then we set that equal to 0 to be able to find the maximum. Doing that, we can take out a factor of pi r and then set each one to be equal to 0 to solve it. So for this pi r equal to 0, r must be 0, or 2 minus 3r is equal to 0, which means that r must be 2/3. Now, in the context of this question, r can't be 0 because we can't have a radius of 0. So therefore, we're carrying on with r equals 2/3. So when r is 2/3, we'll put that into our equation for the volume here. We're just substituting in 2/3 for r and working that through. And that comes to 4 pi over 27, which is what was asked for in the question. Okay, 2a, we've got a fairly straightforward chain rule. So we will bring the 3 down, times it by 4, and then times by the derivative of the inside. So that's that happening. 3 comes down, times by 4 makes 12. Power gets reduced by 2, times by the derivative of the inside. Okay, for b, we have a curve equation of this, which is a quotient. So we're going to use the quotient rule to differentiate and then set equal to 0 to find the stationary points. Okay, so differentiating using quotient rule, we're going to do, first of all, take so this v is the bottom, u is the top. We're doing v times the derivative of u, so the bottom times the derivative of the top. Then subtract the top times the derivative of the bottom and divide it by v squared, the bottom squared. We will set that equal to 0 because we're looking for stationary points. If that's set equal to 0, then only the numerator is equal to 0. So simplifying that through and then setting it equal to 0 looks like this. Now we're going to continue solving. So log of x minus 1 is 1. That means x minus 1 is e, we're raising to the power, both sides e to the power of, so e to the power of 1 is still just e. So x is equal to e plus 1, and you can leave it as that. You don't need to turn it into a decimal, but you also wouldn't be marked wrong if you did. Okay, for part C, we've got the equation of a curve. We're told that the derivative is this much. It's claimed that the curve has a minimum point when x is 3. I'm going to use the second derivative to work out what types of minimum or what types of stationary points we have to see if it is a minimum or maximum. I'm hoping it comes out to say that this is not possible. So that's what I'm aiming for here. So I'll start by rewriting f dash of x in easier terms to differentiate. So putting those into power terms instead of fractions means that I can then do the second derivative. So of that first term here, then we are bringing the minus 3 down, reduce the power by 1. We will times by the derivative of the inside, which is just 1. Remember, 3k is a constant, so that doesn't become anything when we differentiate. Same with this bit here. This differentiates away to 0. It's tempting to try to differentiate that as if k was an x, but this is just a constant because k is a constant. So when we differentiate, we don't get anything here. Now simplifying what that looks like, it's like this, so it's a bit easier to see what we're doing. So whatever k is here is going to get added onto x and then put to the power of 4, which means that will be positive, and then we'll do negative 81 divided by positive, so that will always be negative. So wherever we are on the curve, the second derivative will be negative. Now, if the second derivative is negative, then that means it would give us a maximum. So we can only be looking for a maximum. And the claim was that there's a minimum at a certain place. It doesn't matter where the place is. That can't be true. So therefore, there can't be a minimum when x is 3. Okay, part D, we have some more rates of change. And this time it's on a cylinder where the height is always twice the radius, which means that we can rearrange to say that the radius is equal to the height over 2. Now we're talking about volume, and we want to then put that in terms so it's all in one term, so not this mixture of r and h. So we can use the fact that r is h over 2 to pop that into this here. So r squared is h squared over 4. So then popping it into our volume formula gives us this. The reason to do that is so we can differentiate it to get a rate. So we can work out from that the rate at which the volume is changing with respect to the height. Okay, now we've also been told dV by dt is equal to 30. So that was in the question. If we can find a link between those two, then we can work out the rate of increase of the height. Okay, so we want the dH by dt, the rate at which the height is changing over time, and we need to link these two together in a way that would give us that. So this would be dH by dV times dV by dH. So the v's would cancel out and leave us with dH by dt. Okay, so dH by dV we worked out over here. dV by dt we were given, it's 30. So that comes to 40 over pi h squared. Now, when the radius is 5, which is what we're trying to work it out for, so we want that rate when r is 5, that means h is 10, because we know that the height is twice the radius, so we can put that into this. So dH by dt at that point will then be 40 over pi times 10 squared, or 2 over 5 pi. Okay, part E, we've got some geometry factoring into the algebra that we're doing on this one. So first thing, we've got this curve, and this is the normal to the curve, and we're working with the area of that triangle that's been shaded. So first of all, sorry, I've just skipped ahead a little bit too much. We're working out dy by dx so that we can differentiate this thing here. Now that gives us the gradient of the curve, and we are wanting to know the gradient of this line here, the normal, which passes through x equals 1. So when x equals 1, we can substitute that in to get the gradient in terms of k. And that simplifies to k over 2. Now we want the gradient of the normal, so that will be the negative reciprocal of the gradient of the tangent. So flip it over and make it negative, minus 2 over k. Now, using that to find the equation of the normal, we use our equation of a line, which is y minus the y coordinate is equal to the gradient times x minus the x coordinate. And just take a look up at the graph. This is where I'm getting the coordinates from. So x was 1, y is k. That's a point that is on that normal. So we now have an equation of the normal. Now at B, this point here, that's what we're trying to work out. Y is 0. So if we can put 0 into that equation, we can work out where it crosses the axis. So when y is 0, we get this to be true. Working that through, x is equal to k squared over 2 plus 1. Okay, so now we can do the area of the triangle because we know where this crosses the axis, so we know the length of the base. We need to do half the base times the height. So half the base is just here, that we just worked out as our x-coordinate of b, and the height is the point of this triangle here, which we know goes up to k. So the y-coordinate just there would be k, so our height is k. Now working out, we were told in the question that the area of this triangle is equal to k, so that's why I've set this equal to k now. We can carry on simplifying that through. So k divides with k, and we would get this thing is equal to 1, and then I timesed everything by 2, so we've got the k squared plus 1 bit is now equal to 2. So k squared plus 2 equals 4, k squared is 2, therefore k is the square root of 2. And it's not plus or minus, it is just the square root of 2 because we need a positive value to work out the for it to be an actual area. Question 3, we have another product rule, this time with some trig involved. So differentiating it, we will leave the first term as it is, differentiate the second term, times them together, plus differentiate the first term, leave the second term as it is, times them together. No need to simplify. Okay, on to part B. We're going to differentiate this function and then find when that gradient is the same as this gradient because it will be parallel to that line. So first differentiating gets us this, and then we need to set it equal to the same gradient as y equals x. Well, the gradient just there is 1. So we can set that equation equal to 1 and carry on with solving that. Working that through, we get down to x equals 1/4. For part C, we are looking at when this function is decreasing. That means the gradient will be negative. So we need to differentiate it first. We're using the quotient rule because we've got a dividing thing happening here. So that starts with v times du by dx, so the bottom times the top derivative, minus the top times the derivative of the bottom, all over v squared, bottom squared. Now we want to know when that is less than 0. So rearranging this equation will then look like this. And we go through solving that, we get 1 minus x squared is then less than 0, which gives us, if we're thinking about it in equals terms, if we were to set that as equal to 0, we'll get x equals plus or minus 1. So this gives us the critical points. We just need to figure out which side of plus and minus 1 we need to be. So think of a sketch of this graph here, 1 minus x squared. It's a negative parabola, so it goes like this. We want to know when does it drop below 0. So if this was our 0 line, we want to know this bit of the graph here as it goes below 0 and this bit as it goes below here. And our critical points where it crosses were at -1 and 1. So for the original thing to be true, it'll be happening to the right of 1 and the left of -1. Therefore, our function is decreasing when x is less than -1 and x is greater than 1. Okay, we need to solve an equation to find x, where the gradients of these two things have a product of 3. So first of all, we need the gradients of those two things. So gradient of the first one is product rule. Done heaps of that already. Gradient of the second one is just differentiating e to the minus x. So that's minus e to the x. Now we're told the product of those things makes -3. So times them together, we get -3. And now we're just into solving. So we can divide through by the e to the x stuff, or sorry, rather multiply out the bracket, and the e to the x's will cancel out, and then we get this. So then that becomes a quadratic that looks like this. We can factorize it, and then we get x is -3 and 1. For the last one on this paper, we have this diagram of a graph that's a fairly complex one, and it has a maximum point at m. So we're going to need to try to find that maximum point to prove that tan squared k equals 6. So first of all, rewriting this, this is cos x to the half, makes it a little easier to see what we're doing to differentiate. So now we'll differentiate that thing up there. So we are using the product rule, and inside of it we have some hairy stuff happening. So the product rule will leave the sign cubed as it is and then differentiate cos x to the half. So that uses the chain rule to make this piece here. So that's half cos x to the -half and then times by the derivative of the inside. Right, then we need to add on the second part of product rule. So we differentiate the first piece, which is sine cubed x. That is the same as 3 sine squared x times by cos x. Again, that's chain rule. So we differentiate the sine and then times it by the derivative of what was in that function, which is sine x. And then times by the original of that piece just there. Okay, now rewriting this to make it a little easier to see what we're doing, I've just turned the cos x to the -half into a 1 over square root thing, put the half in with that as well, and similarly over this side. Now for us to get a maximum, we'd set that equal to 0, and then we can rearrange taking this piece over to the right hand side. Okay, now multiplying through, if we bring the 2 cos k up to here, we will get 6 sine squared k cos squared k is equal to sine to the 4k. That's because the root cos times the root cos here makes a regular cos, and then that got times by the cos, that makes the cos squared bit just here. Okay, so now in the question we were told to make tan squared k equals 6. I'm going to try isolate the 6 and hope that it comes out to tan squared. So for that we have sine to the 4k, divide it by sine squared cos squared k over here. Okay, now cancelling through the signs ends up with this, so we can cancel out sine squared with a sine squared up here, leaving us with sine squared over cos squared. Now sine over cos is tan, so this is equal to tan squared k, and we're done.